Hello. Having solved 11a, I thought, well, let's get started on 11c. I've just had lunch and I drank a beer. It turned out to be a strong one, what equivalents 2 units of alcohol. So maybe I won't be able to do it, but let's see how it goes. I have written the definition of eta and the functional equation. And as usual, I'd like to get started with the Q expansion. And we can just trace what happens to the 24th root of Q. So here it's to the 40th. And here it's minus 8 and minus 32, meaning it vanishes. So that implies that the value of at infinity is unity, whatever series come out of this. Working on the success of letting k be 1/2, let's write this. It's an equation where we operate on eta z with s of order 1/2. So it's it's set to minus 1/2. And then we apply this, and then the z vanishes. So it's 1 divided by square root I, eta of z. Then we need to see what happens to eta of 2z. Well, let's first prove that it's invariant under gamma naught of level 4. It's generated by T and S, I think it is. Now, how was it we could write this with alphas and t to some power, and that might come in handy. I don't know. All right. K is perhaps not the best choice. LZ, where L is 2 or 4. Of course, it's invariant by T, so it's only this guy that is. Or should we? I think we should try to apply alpha. Alpha 4 or alpha 2. All right. So let us call that an M. So we know that L and M are 2 and 4. We'll write this M. And let's operate nah. So let us do the transformation instead of the matrix, and then try to do this later to see what k we will use, because we may do each of these with different k to end up with a sum 2. See that? One divided by 4m, that's a given. And so it's 1 divided by 2z. The simple thing is to just use this. And put 2z into z's place. And the same with 4z. And since we have no eta of 4z, I wonder what we can do here. This is the one that's interesting anyway. And it comes when operating with alpha. Of course, if we operate with this, then we are dealing with eta of 1 divided by 4z plus 1. That's a little weird. It's z divided by 4z plus 1. The other one had negative imaginary part. That looked very wrong. So we just add 4 here. So it's square root of 4z plus 1 divided by z times I, the imaginary unit. And this was z divided by I, that cancels, times eta of z. That means we have eta of z we call this gamma, 1/2 equals eta of z. That was lovely. On the other hand, I don't really believe this, because wouldn't that imply that eta squared bind in M1 of gamma naught of 4? This sounds wrong, so I'll just look it up. Or I won't look it up, I'll just check it. Well, that didn't take long. I was a little too fast here, because eta is not particularly invariant under t, only t to 24th. Now, the same trick actually works for 2 here. It becomes 2 down here. And then we can translate it twice. Or the 4, which comes there, then we just get 4 down here and translate it once. Oh, then we get different, I'll just do the details. Now, what did we call that letter? Lz divided by 4z plus 1. You can translate it once or twice, or in this case 4 times. And this then gives square root of Lz divided by I. And then the reciprocal, which is Lz. Now, where did the L go? It should have been under the square root sign. I'll just correct it a little. So now we can use the FL of Z here and operate with gamma of order 1/2. And then the 4z plus 1 cancel. So it's the square root of -1 divided by L times eta of Lz. And that holds for L equals 1, 2, and 4. I have now copied this formula and the function here to the next page. There we go. And all we need to show is that G is invariant under this matrix, and we'll just check when we operate on this, how many factors do we get of 4z plus 1. So 20 minus 16, that's 4 times 1/2. So that means that g of z to order 2 I'm actually very fond of this notation using the formulas with k equals 1/2. That makes it very easy to operate with. Up here we get L, that's unity, we get nothing. Down here we get I to 20th and to h, though we don't need. Actually, I was a little worried about the branch, because here we are with positive real part. I said it's square root minus 1. Oh, so I don't know if I should use minus 1 or plus 1, so I'll just write that. I really don't know it's plus or minus. But it doesn't matter as long as it's to these high powers. When it's 4 or above, then it doesn't matter. Now this is, that was just eta of, oh, that was 2z, so it's 2 to minus 1/2. So this is unity. This is just eta of z to 8th. And here we have 4 to minus 8/2. This is 2 to 10th, and this is 2 to minus 8, minus 10th, minus 8. So I'm actually a factor 4 off. Well, let's leave that for the time being and then look at the cusps. So we take the cusp z equals 0. And now we must apply the transformation rule as it is. I'll write it down here. Z, oops, this is minus 8 and minus 8. So it sets to 10th minus 8. That the sets cancels. Very nice. And the imaginary doesn't matter. So we have two to minus 10 times 2 to 8th. That's very interesting. And now, what did I do with the, I didn't expand the series, just showed that it was 1. So this one will give 1 plus something with Q4. So it's minus like 8Q4, etc. Because it's to the 8th, I think we get 1 plus 8, and then we make the series and expand, so it becomes 1 plus. So that's the lowest term we have. And all the others are, of course, multiplier of Q4. And that means that G of naught equals 1/4. Oh, I thought this was wrong, but I believe that was not what we got. Well, I'll have to look it up afterwards. And the last one we need is Z equals 1/2. So this guy maps infinity to 1/2. I wasn't doing it in such generality. No, I was not. And the force Z, we have the same problem with force Z, which we had in problem 11a. And right now, I really need a cup of coffee, and then I'll check up how I solved this one, where we get the 4Z. Oh, there we had a transformation with 4Z, which we don't have now. Oh, so the transformation formula here is much more simple. So maybe we can just go ahead and do it. And we use the transformation formula. Now, where did the 2Z come from? It should be, here we are, it should be 2Z down here. So we subtract 2, so we get minus 2 here. And that was, of course, the more difficult one. But I need to go through the details, and that requires a cup of coffee and a sheet of paper. So my program for now is to do it all, first make coffee, and then do it all on a distinct sheet of paper, and then compare that to what I've got here, and then I hope I'll be able to conclude something at the end. First, I verified the invariance, and T we already had, but then also under the other generator of gamma naught of level 4. And then the value of at the cusp 1/2, and you can see at the end I evaluate the power of Q there, which turns out to be 1, so the value at infinity is 0, or the value of 1/2 is 0. And then finally the value at 0, which turned out to be 2 to minus 6. I tried to make a general formula, but it seemed to be the safest way to make each calculation in its own right. Now we have the function, the results here. Oh, there's also the value here, which is that's it. Was the f of naught. So we have t to a q, the powers of q24. It's 40 minus 8 minus 32. Oh, it is unity. Well, so these are the results we get. Unity at infinity, all right. And here they differ, and here they both are naught. One of these results is wrong. I'll just have to look that up. But now we can solve the next problem of... but I don't like that this picture keeps vanishing. That's annoying. So we need to compare the powers here to see that the relation, one of them will have lower powers than the other. So, and then the argument will, we can actually prove that they have the same. Because the relation between them is modular form of order naught, therefore it must be constant, and it cannot be naught because the value of infinity tends to unity. So we just need to compare the value of theta and then the guy they compute. So theta at infinity is unity, and eta to 5th of 2z divided by eta squared of z, eta squared of 4z. Then the power of q24 equals 10 minus 2 minus 8, which is naught, so it gives unity. And that means that this function tends to unity for z tending to I infinity, which means that the constant must be 1. So the answer to 11D follows immediately. I just need to find the mistake in the value here, and then we are all set to go on.